So interesting. Okay, so maybe we should get started. So welcome everyone to the last seminar, I guess, of the fall. I'm really honored to introduce Dr. Ahmed to you today. And I'm just going to give a little background. Sheehan did his undergraduate at Fordham University, right? I think you worked on like condensed matter theory modeling, right?
I did, and truthfully, the actual thing I got from that was I learned I should not do research in condensed matter. Which I still always advise my students, like, hey, if you don't end up liking a certain research, you still gain something from it. You know, like your focus is somewhere else.
It's so important, right? You don't
I did do all my summer researches were condensed matter stuff.
Yeah, so that's cool. Yeah, so then Dr. Ahmed went to Rutgers, New Brunswick to do astrophysics, and let me read the title of his thesis if my phone will. So it says, an investigation into the effects of baryons on satellite galaxies and cosmological simulations.
Right. This was, hey, we have many galaxies around our Milky Way galaxy and others. Our theory says there should be many more. We don't see many more. This was kind of like all the stuff that you and we all worked on similar simulations. Answer to the thesis was complicated. We don't really know.
Like so much
yes.
Research ends up, right? Excellent. Yeah. So then he taught at Lafayette College for a couple of years before joining us here at Rutgers-Newark, and in fall 2019, which is when I also joined. And I remember meeting you for the first time at the new faculty lunch or something.
I don't think I understood who you were or that you joined newly, but yes,
I did. I remember. I think there was some free thing they
gave some sort of training.
Yeah, and then a free something. Like we couldn't figure out exactly what it was.
Yes, right. We all went to that other building, like not on this.
Yes, it was some other building. I don't even remember. But anyway, so yeah. So anyway, since then he's become really a key member of our department. As you well know, had a very important role in establishing our undergraduate introductory level physics and astronomy. So with astronomy, let's say first, like he developed and implemented impressive curriculum material kind of from scratch. Which and I guess John, I joined the teaching.
I joined 3 weeks before the semester started, and it was like, hey, we don't have an astrophysics.
Right, exactly. So this is very nice. And in physics, he's joined in the physics side in the intro, algebra-based and clock-based physics with Diane and Josh. They're one of the top teams, I would say, in the country, leading the investigation, the teaching of the pedagogical approach through ISLE, Investigative Science Learning Environment, where they also are very active in research with this method and the effectiveness. And Sheehan has presented at various conferences. I guess regularly present.
Yeah, we go to AAPT.
Yeah, AAPT with different aspects of this, as well as published several publications on this in the last few years. Co-organized workshops in the area so that other teachers can get involved. At the same time, part of his heart is still in the skies, I would say, right? Yes. And so he has been, apart from the teaching of the astro, he's this has been very lucky for our department because he's led stargazing nights for us. He's the artwork around our department. He has are coming from his images from his telescope,
which is kind of what you'll see.
So he'll tell us more about that today. So maybe I should just turn it over to you.
Do you guys mind if I darken the room more than normal this time? Because lots of photos that have a dark background. Tell me if this. Whoops, John, how did we do this? Oh, thank you. And one more. Okay, if this is too much, the windows I think can stay for you guys. It's not affecting this. Is this okay?
Yes, it's great.
Okay, don't fall asleep. Okay, so this talk's going to be a little bit different than the other research talks that you guys might have experienced. This is a little more personal. I'll kind of take you through my specific journey of astrophotography and figuring all this out, and hopefully hey, you guys can do some of this also. I think everyone can. I've roped John into this, my colleague from grad school and teaches astro here. You've kind of started doing some of these things because of the conversations we have. Okay, so let's, ooh, this works. Cool. What surrounds astrophotography for me. It is a combination of I love photography. If you've all seen me walking around with my camera in the department, I do that a lot. It combines like, hey, space science. I've always did my PhD in space stuff. In third grade, my vision got blurry, and I need to get these things, and I hated my mom for it for a little bit, which was very mean because I was like, this is genetically your fault. But as a kid, I was like, I need to understand what's happening. So I really got into optics because I wanted to know why my eyes were not working good. So this, again, combines a lot of things. I love computer stuff, tinkering with electronics. This has so much of this. Image processing, lots of like learning how Photoshop works and computer stuff works. Also an interest of mine. Just trying to become a better artist. This part's incredibly hard for me. I have no natural talent in this. Like my wife, who's an artist, she'll just take a photo with her camera, and I'm like, with her phone, and I'll be like, how is your composition so much better? Because I just don't innately have that. Also, this comes with a lot of that. Cannot explain how much both physical and mental anguish comes with trying to do astrophotography. Technological frustrations, computer frustrations, and it turns out skies are clear when it's cold, and I am not genetically built for being in a cold environment. It really sucks. Okay, so kind of like the theme of this, did you guys grow up looking at books that had Hubble Space Telescope pictures? They're like the covers of physics books. I remember in high school, I'd like sit in the library and there would just be these like big print books with immense like pictures of galaxies and nebula, and I'd be like, this is nuts, right? Like, so all of this kind of started with that obsession. This is the Hubble Space Telescope. It's the size of a bus. It's in orbit around Earth, little cross-section view of what everything does. It's been up there since the 90s and is still running. Parts of its equipment have failed, parts have been repaired. It's still going. It is crazy that something has been going on for 35 years and is still producing science. This is an incredibly famous picture that you might have seen. This is Hubble's deep field taken in 1995, pointing at a completely black patch of space for a few months, and suddenly it's not black. It is filled with, these are not stars, these are galaxies. Each contain 200, 300 billion stars. We're beyond where numbers make any visual sense to us anymore. This is another incredible one. I think everyone's seen this. It's the Pillars of Creation. It's these very dense nebula clouds where the fun thing is, these are new solar systems being formed. These little things are new gas coming together, forming stars and planets. Just before we move on, hey, do you see the weird step shape? This is because Hubble actually has 4 cameras, and 3 of them are the same, and 1 of them is different to get a more zoomed in view. So that's why Hubble's pictures often come out stepped. When they combine all 4 cameras, it's just how it works. So that's why you'll see a lot of pictures that look like that. So again, I'm priming you guys for just what kind of inspired me to get into this. These are pictures taken by Hubble. This is 12 million light years away. Didn't put a distance on that one, but these are multiple millions of light years away, different galaxies. A galaxy with an active galactic nuclei, a black hole that's spewing out material that is itself bigger than the galaxy. Lots of cool stuff. So yeah, this is the big bus-sized telescope taking all these pictures up away from the haze of the atmosphere up there in orbit. Let's come back to Earth. Typical view. People have seen this kind of night sky in New Jersey. There's the moon. What sucks is our eyes are at the threshold of sensitivity to see these things. If our eyes were like 50% more sensitive, we'd be able to see some of these galaxies and nebula up in the night sky. We are just at the limit where we can't see them. Sometimes we can get hints of them if you're in an incredibly dark rural area with not a lot of light pollution. So for example, the Andromeda Galaxy, which is the closest galaxy to us, if you imagine it, how big do you imagine it in the night sky? This is interactive. You're free to talk to me during this. Little thing.
Yeah.
It's that big. That's the moon. And you are at the threshold of not being able to see this, and it's 3, 4, 5, 6 times bigger than the moon, depending on how you count the edges. I wish we could see this all the time, just have this terrifying, gigantic moon moving over us that's going to crash into us in a few billion years. You can. If you go to really dark areas, you can just get a hint of there's something fuzzy there, but it's never good. It's never like this. However, so as you keep in mind as we look at these photos, most of the photos that I'll be showing you are about this size. So multiple moon diameters in its apparent size. So given that some of these things are multiple million light years away, some of them are only 1,000 light years away, I do want you to kind of imagine these are massive in scale. These things themselves are many thousands of light years huge. Nebula, not this thing is much bigger. Cool. Okay, so how do we make these dim objects show up more? Well, like I said, our human eyes and our rod cells, which are the ones that are sensitive to light, can effectively detect one photon. So we're at the threshold. There's nothing better we can do with our eyes too much. So, hey, let's make the holes in front of our eyes bigger. You have your pupils that are about 1 centimeter. Maybe they grow to be a little bit bigger if you're in the dark for very long. But guess what? What if you put a funnel in front of your eyes? And hey, those are called telescopes or binoculars or whatever other fancy name you want to give them. But it is effectively a light funnel. It's just capturing more of the flux and funneling it into your eyes. That's what telescopes, cameras, and lenses are. And then, well, maybe let's not use eyes. Let's use a camera sensor that can actually hold onto these photons and let them build up. So instead of just detecting the one photon, why don't you keep it open for a long time, for many seconds, and collect all the light. Okay. Into collecting light, pixels on a camera sensor. We're going to be talking about camera sensors a lot today. You can think of them as buckets. You can think of photons coming from these things as rainfall coming towards us. This rainfall of photons falls into these buckets. The buckets convert them to electrons. And these electrons are hanging out in this well until the well fills up and we take them all out, and every bucket gets a certain value for the number of electrons it has. And that's what an image is. It's just brightness values, basically, at every location on your image. How do we get colors? Well, almost all the cameras that you own in your phone, in your iPads, in your computers have what's called a Bayer filter. Every pixel has a red, green, or a blue filter on it. So every pixel isn't actually collecting all the light. Red pixels collect red light. Blue pixels collect blue light. Although I want you to notice something over here. What do you notice about the number of red pixels versus green versus blue? Just quick glance at the number of dots here.
More green.
More green. Almost every cell phone camera, every monitor that we have has an RGB pattern. Two green pixels for every red and blue. This is to emulate how human eyes work. Human eyes are the most sensitive to green light. So if you have the same intensity of green and red light, humans will pick out the green as a brighter picture. To emulate that, all of our cameras and all of our television screens are built with this RGB pattern. This will eventually become a problem, this emphasis on green. So we're already moving into human perception controls how we experience these things, and we're no longer purely in a scientific process. Some of it is being manipulated to make you see what you like to see. Okay, so let's grab a camera and a lens. These are common things that people have or can buy. And let's take a long exposure photo. However, before we do that, maybe we want to go to a dark area so we get to see things clearly. So let's hike to a remote salt lake in Utah. Let me do something stupid with my friend and dip my hand into a literal hole made out of salt. This is very dangerous now that I look back at it in retrospect, being so close to an edge of a pit of salt water. Let's avoid some snakes, wait in the dark in the bushes. Let's set up some photos. This is not me. This is my friend and our colleague Jesse, who teaches at Swarthmore. I don't have a lot of pictures of myself. I have pictures of other people doing things with me. Let's take a 30 30-second exposure. Let's open our cameras for 30 seconds and collect all the photons coming from the sky. Oh, we need a tripod. Okay, cost, right? Camera, lens. Now we're adding a tripod to keep all of this stable. So in those 30 seconds, your camera doesn't move. And let's see what we get. This comes out. Where's our feeling up? Like, truthfully, how do we feel about this? Okay, maybe.
Very cool.
Very cool. Sure.
Is it day or night?
This is night. This is full night. Hey, what is this? What do we think this is?
Can you move to the left? Okay, so
A lighthouse.
That's the moon. Because it's a 30-second exposure, the moon is incredibly bright, and all this light you're seeing reflecting off of the salt lake is moonlight reflecting. So, certain things we can see. That's our Milky Way, or the band of our Milky Way. You can see a little bit of dust and dark dust lanes visible. There was a meteor that was falling during that time, during those 30 seconds, bless you. And it left a trail behind. Great, cool. Everyone's happy with the photo. I'm not happy with the photo. Let's pixel peep as, so this, let's see if this works here. Okay, the more I zoom in, which is what I do in a lot of my free time with photos. Stars are no longer little spherical dots as they should be. Do you all notice that the stars are elliptical, oval, elongated, and if I go to the corners, it gets worse? Well, what's happening here? So these are issues. Elongated stars. Now, at the edges, this is because of the lens. How do you fix this? Well, you shell out a few $100 more to buy a better lens. Okay, let's not get there. Everywhere else, the main reason the stars are elongated is our Earth is rotating. So if you keep your camera on for 30 seconds, in those 30 seconds, the sky apparently moves. So you will always get stars trailing. So we're at a weird problem, right? Longer exposures mean brighter images. Brighter images means the stars move more and your image gets messed up when you zoom in. Well, this is a weird problem. So what's our solution? Well, we make our camera move in the opposite direction. So, hey, that looks like red. That's Earth. It has a rotational axis. It points broadly towards a star called Polaris. Earth rotates eastward, as we all know. That's an exaggerated version of what I'm taking the picture with. Well, why don't I tilt my little camera pointed towards the same axis that the Earth rotates around, and I make it rotate the other way. So I am fighting the Earth with my camera. That's what this thing looks like. So I started off with the typical camera, a cheap lens from the 1980s, and I had to spend money to get this thing. Okay, so this is going to rotate against the Earth. If your camera is bigger, if your lens is bigger, you need to buy a heavier version of these, and these turn into multiple kilograms, 10, 20, 30 pounds is what we're talking about. This is where the physical anguish comes in, when you have to take this and bring this downstairs when your hands are freezing in the cold. Okay, so typical night, New Jersey. This is 2018. This is after all these things. Like, okay, let's test out a motorized mount with that same camera. Lots of light pollution. You can see, do you guys know Orion, the constellation? It's hard to see here, but you can see Orion's belt here, the sword hanging down, the shoulders. Hey, the Subaru logo is right there. That's the Pleiades, a set of 7 stars. And let's take a 15-minute exposure now, because now we can do that without the stars trailing. Let it build up. Oh, look. Things are showing up. Let's zoom in and brighten stuff. That's from a 15-minute single photo that's been brightened up a little bit, taken with a typical camera, except it was on a motorized mount, so we could just keep it open without problems happening. So where are we? This is a Hubble's picture of the Orion Nebula, and this is me zoomed in on the same picture. Getting there? Like, we can see it. Like, look. I did this and my whole brain changed, because I'm like, okay, these things that I grew up looking at that I thought was only accessible by experiments funded by whole countries, I'm not there, but this is not half bad. This is cool. I'm getting colors. I'm getting the blues and the reds. What do the blues and the reds mean? Reds are hydrogen emission, blues are oxygen emitting. So I can already be like, hey, there's hydrogen here, there's oxygen on the wings, and starlight reflecting off of dust over here. Cool. Okay. However, there are issues with long exposures, which is the long exposure itself. While taking this kind of motorized exposure, if the earth moves, if the ground shifts, or if you accidentally bump your tripod, we're back to having these kinds of problems. Your stars get all bent and weird. So, and this will happen. If you try to take a 2-hour exposure, there's no guarantee that someone's not going to accidentally bump your thing, or a truck drives by and the ground vibrates just enough that the stars move. You could spend 3 hours taking an amazing photo and one truck drives by and that's it, your photo's ruined. Your whole night is wasted. So we don't actually end up taking super long exposures. What we do is, oh, and another thing, if during your exposure, someone's like, oh, hey buddy, what are you doing? And brings out a flashlight. It hits your picture, that's it, the picture just turns white. This has happened, right? Stray light sources, somebody turns on a garage light while you're doing this next to your telescope. That's it, all gone. So taking gigantic long exposures, while in an ideal case great, doesn't really end up being practical. Let's talk a little bit about camera sensors and how all this works. So there's a nebula, it's raining down photons, we call them DSOs, deep sky objects. As we said, each pixel on your camera is like a bucket, so I'm simulating 5 pixels over here. And let's see what these pixels do. So the photons fall into your pixels, and you get a bunch of electrons that fill up these pixels. And there's circuitry underneath the camera that reads each of these off. Typical 8-bit images goes from 0 to 255, so 256 values off brightness or the number of electrons or height, however you want to look at this. Now, if only the world was this simple. Everything is above 0 Kelvin. There's random movements. Electrons are moving around randomly because of thermal energy, and those electrons end up in your buckets. So your real bucket might actually have some random noise in it along with the actual photons that came from your DSO. We really care about the red stuff. And unfortunately, every time you take a picture, this noise is different. It keeps changing. Although this will be our solution to get rid of this noise eventually. So what do? Well, you take a longer signal, you take longer exposures. Why? Because if the noise is staying kind of down here in the 1 to 2%, if what you want is bigger than that, it's already more significant. Your signal is stronger than your noise. That already makes things better. So longer exposures lead to signal to noise ratio, but we're at this weird threshold, right? Long exposures good, too long exposures bad, too short exposures bad. Finding an ideal exposure in the middle is difficult. If you also go too long, you can overfill your bucket, and this is what's called a blown out photo. If you've ever taken a photo of a very bright light behind someone and that part just becomes white in your camera and there's no detail, that's blowing out. It can also leak electrons onto the other buckets next to it and ruin more and more. That's what you call bloom, blooming effects in images. Okay, other problem is light pollution. We can't always go to a dark site. We can't go to Utah. Have you looked at New Jersey skies? What color do they look like almost every day? It's like an orangish pink thing going on. Our brains kind of cancel it out, but you just can't see a lot of stars. So light pollution is another random source of photons that fall into our bucket. Let's do this. Oops, that went too fast. They fell, and now more randomness on top of the randomness, and your signal's getting hidden in the noise. Every time you take a picture, things are different. Look how it keeps changing, sometimes more, sometimes less. Your signal's kind of mixed in there and you're never getting to see it. There's other problems. Cameras aren't magic. There is circuitry beneath the camera. And guess what happens to your computer when it runs for too long? It gets warm. That circuitry gets warm. Well, that warmness now introduces extra electrons, extra signals into just where the circuitry is. All of this is called amp glow. I think I went a little bit There we go. This causes what's called amplifier glow because the circuitry is almost always mainly an amplifier. Okay, so let's see. What do we have? We have the red thing, that's our actual signal. We have the gray stuff, that's sensor noise, and it all keeps changing. We have amp glow, that's the green stuff I put in there, and our old friend light pollution. So we're kind of going to take the next 10 minutes and go through how we get rid of all of this to just keep the information that we are getting from space. Okay. When you take this picture that has all this garbage along with the stuff you want, this is what's called a light frame. You captured light. Good light, bad light, fake light, but you captured light. This is a light frame. This is what a light frame looks like. Long exposure. You can see stuff that you wouldn't be able to see before. Like, at a certain point, I was happy with this picture, right? This is great. This is insane. I can't see this with my eyes. However, do you notice all the issues with it? So this is 300 seconds, 5 minutes, 5-minute exposures. Do you see all the noise, right? That's a bad high noise image. There's the amp glow. That's where the circuitry for the camera, for the chip is underneath it. Here's another example. You can see it much better. Yeah, sure, there's space stuff, but it is so made ugly by all the noise and looks like there's a star. That is not a star. That's the circuitry in the camera messing everything up. Okay. Now 600 seconds, 10 minutes. Okay, so let's focus on the stochastic noise first, the parts that are random, because random stuff is easier to delete. So how do we get rid of random noise? This is a process called stacking. You can think of it as averaging. If you are getting data and there's some random noise in your data all the time, combining all your data together and averaging can take out that random part, or at least bring it to a value that you can end up subtracting. So stacking is this whole take multiple short-ish exposures, combine them together using software. This is free software you can download on the internet. I don't have a list of them here, but if anyone's interested later, I can give you guys ideas and links. Now, this isn't going to show up great over here, but because resolution and projectors, but this is a noisy image, one single exposure. Once you take 12 exposures and combine them, this is hard to see, but it is in the blank spots, it is much smoother. And this is much more visible when you're actually looking at it on a screen and not a projected view. Notice the trees are blurry because the camera's following the sky, but that means it's not following the stuff on Earth. So now you can get to multi-hour, 10, 20-hour exposures as long as you keep each single light frame 30 seconds or 1 minute or something like that. There's another advantage to doing this. If you are taking 1 minute exposures to add up to multiple hours, if somebody pulls their car in while you're doing this, you'll lose 2 of them, but you haven't lost the whole night's work. It really lets you reject out anything bad that happens. Okay, so when you average this all out, you've kind of taken out sensor noise. I hesitate to say you've taken out light pollution. It is random. You've taken out the randomness of it. Light pollution really messes stuff up. I'm pretty sure I have to click here to make this work. So this is showing how, as you average stuff over time, the signal, so there's an object right in the middle. As we stack more and more things, time 13 minutes, 14 minutes, 15 minutes, are you seeing there's a little bump showing up here in the signal? All the noise is being gotten rid of. Your signal's showing up here. This is a light polluted area, and the same process has happened. The same process is happening, but it's happening at a much slower rate. Notice the time. We're at 46 minutes. Can you really tell if there's any shape to this graph yet? And it should end up with the same shape here. An object creating a bright spot right here, nothing here. It just takes longer. So this is how bad light polluted skies make everything. This shape came out within like 10, 15 minutes. And to get an equivalent shape, we are at over an hour now and nothing is happening. You're going to have to do 5, 6, 7, 8, 9, 10, 11, 12 hours to get the same quality that you get at a dark site. Nothing beats, no amount of mathematics beats just going to a place where bad light isn't coming into your image. Okay, we can't wait for this forever. Okay, cool. All right, so hopefully we've gotten rid of the stochastic part. Now we need to get rid of, how do we get rid of this glow from the circuitry? Well, you take what's called a dark frame. You put a little cap on top of your camera, and you turn on your camera for the exact amount of time that you would have turned it on to take a light frame. So no signal is coming in, and the only thing you should get is the glow from underneath the circuitry. So you put a cap, you take a picture, all you get is the random stuff always there and the glow from the circuitry. And what does that look like? Like that. So you have a picture that's only the bad circuitry signal. Now you can just subtract it. Pictures, remember, are just numbers representing brightness at every single pixel. So you can just subtract out. You'll be like, okay, I'm just going to subtract out these high number values from this area. Everything will be pulled down. So you subtract out a dark frame, and that will hopefully get rid of it. The other thing is you can cool down your camera. So now think about the cost again. Well, now normal cameras don't work. You need a camera with a cooler in the back because thermal noise doesn't go away, but it decreases as you cool your camera. Okay, so we can subtract this dark frame. Cool, that's done. Hey, we're there, right? We're almost there. There's more problems. There's always more problems. That is the life of astrophotography. The fields are not flat. What do I mean by this? So in a real camera, you have tubes, right? The whole structure of the lens and the camera are here. And these tubes, what they end up doing is blocking some of the light from the edges. And your photos always come out a little darker at the edges. Again, anyone into photography knows this. When you take a wide angle picture, there's vignetting that happens. It even happens in your phone cameras. Your phone adjusts for all of this, just like we can. And how do we do this? Well, we take a picture of a uniform light source and see what the photo comes out as. Let's look at one of these things. This is called a flat frame. This is how I do it. I like this photo because it looks like a UFO. But this is my telescope. This is a thing I've taped together. It is a uniform light source, and you take a picture of this uniform light source. Big telescopes, like the ones that are on top of mountains, they don't have a thing like that. They just point to the evening sky when it's like before night, when it's just glowing a little. You find a uniform patch of the sky, and you take a picture of that, which is very cool. And here's what a flat frame looks like. See, bright in the middle, dark around the edges. So how do I fix my photo? Well, I'm going to need the dark parts to get brighter and the bright parts to get darker to balance it out. So I am going to divide the image by the flat frame, that's hard to say, values. You divide by small numbers, it brightens it. You divide by big numbers, it lessens the brightness. Cool, the fields are now flat. Your image shouldn't have weird darkening around the edges. You stack many, many short exposures together. All these frames corrected for all the things that we talked about. We call these calibrated frames, and you get your picture. When you zoom in and you're still not happy, what's everyone's issues with this picture?
It's green.
It's green, and yeah, there's lots of green patches, but you see also the shape of these patches are like streaks.
Mm.
That's so bad. This is called walking noise. This happened to me. I was like, I did everything right. No one told me this would happen. Why are all my pictures absolutely awful? Why does walking noise happen? Okay, so what I have is, imagine this is the grid of your camera, all the pixels. This is the picture you're taking. You've lined up your camera with the Earth's pole. It should counteract the Earth's rotation. However, you are only human. your lining up is never going to be perfect, no matter how much you do. Overnight, the ground will shift a little bit. Your alignment gets out of whack, which means as the night goes on, your image slowly drifts through your picture. You can never get it perfect. All of the little errors that accumulate in that drift pattern, and it leaves these streaks. How do we fix this? We can't we're doing this with off-the-shelf equipment. Maybe Hubble Space Telescope doesn't get this kind of drift error because they're in space, and once they set their thing and they've set it to sum of forces 0, nothing is going anywhere. We can't do that. So our solution is we move our whole camera and telescope randomly as time goes on. So take a picture. Take a picture. Take a picture. Why are we moving it around like this? We're hoping now the drift is not in one direction. It's in every direction. When you average things out, you can kind of hide any problems like this. This is a process called dithering. The term comes from, have you guys seen old drawings like this, where if it's like only 2 colors and they'll use dots to make a shading? This process used to be called dithering. Old comic books use that. But because you are doing things differently at different positions, that's where this terminology kind of comes from. Okay, so I want to catch us up to where we are now. So we need a mount to counteract the Earth's rotation. We need a telescope, big funnel. We need a camera. Why is the camera looking weird? Because this is a camera that has a cooling unit attached to it, so it doesn't look like normal human cameras anymore. It's a weird thingy. Oh no, why do we have a small telescope on top of our big telescope? Well, if you want to dither, you want another telescope to focus on a star and keep it locked on and use that as your target to move around. But your main telescope is taking pictures and it can't do that. So now there's a baby telescope on top of your telescope to do all of this dithering. What does a baby telescope need? It needs a baby camera. Do you want the baby camera cooled or not? Oh God, how much money do you have now? And now you need a computer to control all of this. Can you leave your computer out in the cold? Will someone steal it? I don't know. These are all things I need to worry about. How does all of this get power if you're out not near your house? How do batteries work for big things like this? Not even going to touch that. But this is kind of what you see in a camera. This is the dithering happening, and it's tracking what directions it's moving. This is the picture you're getting. Anyway, just a little insight. Okay, something we need to talk about is I've talked about brightening our images to be able to see them, but the official term is stretching. So when you actually truly get a picture out of your camera, it looks like this. I promise you there's something here. Do any of you see it? No. Diane, you can see it. Wait, follow my finger. You see this? You see a little bright line here? Okay, this is what it looks like. So there is information there. However, the difference between the bright parts and the dark parts is not enough. You need to increase this difference. And I also want you to keep thinking about one of the things in my blurb on the poster said, are these pictures real? This is the real picture. Now, when you have any of you ever taken a selfie or a photo of someone and increased the contrast or color or anything like that? Is that photo real now? Where does your morality lie in terms of judging picture truthfulness? So keep these in mind. So we increase the contrast and brighten up the picture. That is stretching. If anyone knows how brightness curves work, any photo editing software will give you pixel brightness versus a histogram of the number of pixels. And the curve itself, I've always understood how this works, but writing this down, I had to quantify it in physics. I realized this line that controls everything is in a completely different phase space than these two things. This line is showing output brightness versus input brightness. You crank this up. So anything brighter has become brighter, anything darker has become darker. That's all this means. So we're going to stretch the image. Let's stretch this image. So all that information was there. I have just enhanced the differences. Notice in enhancing the differences, I've also enhanced the problems. All that stuff. So this is not a calibrated frame. We'll see the whole process now. Okay. So let's try the main steps. This is called post-processing, right? You spend half your time out in the cold, carrying heavy things and hoping all your electronics work, and then half your time back at home, toiling over a computer, fixing all your pictures. So we take a light frame. We remove amp glow by subtracting the darks. We flatten the field, make the image uniform by dividing by the flats. We stack many of these calibrated light frames. We've corrected all the errors. We stack them together to get rid of any random noise. And then we stretch the stacked image to make the details out. So let's go step by step. Here's a a light frame that we have seen. Pretty okay. Subtract this dark frame. Divide by this flat frame. Repeat and stack. And this is what comes out. Slight improvements. Again, for people who don't pixel peep photos, this might not be obvious, but I want you to look at the plane parts. You notice how much smoother they are? The stars are not getting mixed in with all that noise. And let's stretch it. Yay. So this is a few thousand light years away. It's called the Elephant Trunk Nebula because that looks like an elephant trunk. It has an actual official designation that I don't remember. But we have captured dust in space, gases glowing. Can anyone tell me why the picture is red? Why is it so red? Okay, what's the most common thing in our universe? Hydrogen. Have you ever noticed if you've ever done that experiment where you heat up hydrogen in a tube and it glows? It glows red. Hydrogen's main transition is from level 3. Electrons jump from level 3 to level 2, whichever way you want. It mainly gives out hydrogen alpha emission, which is red. Most of the universe is hydrogen. Almost every nebula in space is red. Truthfully, every nebula picture should actually look like this. It's not that there aren't any other chemicals. There's oxygen, there's sulfur. All these things are glowing with different colors. They are just not there enough. The hydrogen overwhelms any other color. And this is where we're going to start talking about a little bit about how color processing works. I want to know where the oxygen is. I want to know where the sulfur is. I want there to be more color aesthetically than just red, even though red is truthful. But it is also truthful that there are things in there, and just because our dummy human eyes can't see them doesn't mean they're not there. So we're going to bring them out. Before we go there, I do want to talk a little bit more about light pollution filters. So there are filters that can cancel out light pollution or absorb a little bit of light pollution. Now, this only works if light pollution comes from only certain wavelengths. You can use thin film destructive interference filters, which is something all of you have done in physics at some point. So you'll get these filters that you can buy that let light through in these wavelengths, but don't let light through in the 500 to 600 nanometers. That's where a lot of the sodium vapor lamps, those yellow lights that are all on the roads. Until recently, have you noticed our lights are changing in the cities? These sodium lamps have become less and less common because this is not a joke. I have such strong opinions about this. How many of you drive at night? How many of you drive back at like 6 p.m.? Do you get the blue headlights just burning your brain out? Have you noticed that it has gotten worse? Do any of you guys own cars with LED headlights? I beg of you, if you do, please get them calibrated and point them down. For the love of God, there's no regulation in the US about this. And please, I have orange sunglasses that I wear when I drive home. They do work. Orange will cut out a lot of the blue. They work a little bit. You can't cut out the brightness too much because it's night. So sodium lamps are being replaced by LED lamps. So back in the day, light pollution filters, 2 years ago, light pollution filters worked immensely well. Nowadays, they don't because LEDs, at least the ones they use in the roads, are much broader wavelength. So you can't just cut out every wavelength. Then you're just cutting out the picture. Also, like cooler lights are aesthetically ugly. Warm lights, give me warm, cozy fire. We're built to get 3000 Kelvin black body radiation. That's what makes our brains happy. I've talked to you about such strong opinions about this. So there are broadband objects in space that give out colors of all spectrum. You really need to go to a dark area. You cannot cut out light pollution anyway that will harm these. So I don't really take a lot of pictures of galaxies because of this exact thing. I take a lot of pictures of narrowband objects like nebula because they only give you light at certain wavelengths. They are only made of hydrogen, oxygen, sulfur, and a few other things. Very particular wavelengths of light. So what I mainly use to take pictures. Hydrogen and oxygen are the most common things. They give up very specific wavelengths. So I'll use filters that only allow those wavelengths in. Oxygen being blue, hydrogen being red. Notice I am not using the green part of my camera, which is 50% of my camera. Oh no, if I want to improve astrophotography, now I have to get not normal colored cameras. Oh no, those cost more money again. Hydrogen, oxygen, hydrogen, oxygen taken with each filter. See, now you get, this is interesting. Now you can tell. It stopped moving. There we go. The hydrogen is here. The oxygen is a little bit farther away from the shock wave. Why? Astrophysicists will study this and figure out what's happening with the different substances. So, okay, you got your hydrogen data and your oxygen data. I have them twice for a reason, because now you have to turn it into a color image. Well, hydrogen, red. Oxygen, what do you do with that? Well, oh, there's RGB. There's 3 things on your screens. Well, why not? There's less oxygen. Let's boost it up by giving it 2 different color channels. You combine this, so you put H in the sequence RGB, you put H, O, and O. This will be called an HOO image. And you combine them together, and what do you get? Something like this. Notice, not true color. I've only taken reds and oxygen became blues and greens. Truthful? Yes. But also, as our eyes would perceive it, no. But our eyes don't perceive truthfulness in the universe anyway. Why should we use that as a judge for truthfulness? This is the substance. Like, if you interpret this, red is where hydrogen is, bluish green is where oxygen is. Yes, that is absolutely true. If we had different eyes, we'd be able to see this. So as I said, I'll skip through this a little quickly. You're wasting these green pixels. So what's the solution to this? Well, you get a black and white camera and you start taking images with your own filters. You have now gotten to a step where you have to buy multiple filters and switch them out, and the pain and the anguish and the money keep moving. So anyway, hydrogen and oxygen, now you can start doing sulfur. Sulfur is another common element that is present in these nebulae up in space. Let's play this for a second. So this is a thing I got recently. We're catching up to where I am now. There's the camera chip in the back, and those are my 7 filters that came in from China through the tariffs. I don't know how. Don't ask me. I don't want to investigate too much of how they got that in without paying tariffs. Blah, blah, blah. Anyway, now you have to control this with the computer. What if it fails in the middle of the night? Then everything goes. The more things you introduce, the more complicated everything gets. Okay, so how do we map this into RGB? Hydrogen, red. Sulfur, a little more red than the red of hydrogen. Oxygen, solidly in the blue area. Okay. Our weak, broken, dumb human eyes cannot distinguish between these 2 colors. However, do we all agree physically these are 2 different wavelengths? Just because we're not good enough to see it doesn't mean it doesn't deserve to be shown. Well, what do? Well, I have 3 and 3. Well, let me just map one onto the other. Well, hydrogen standardly gets red, so put all your hydrogen data in red. Oxygen, blue, we associate blue with oxygen a lot. Now we're getting to the subjective part of all of this, although it is in the bluish-green 500 nanometer wavelength. What do you do with sulfur? Even though it's like 670 nanometers, which is very in the red threshold, we put it in green. This is how our eyes are being tricked by TVs. This is what we have to work with. So what you get is now what's called an HSO image. So whenever you see astrophotography pictures with those labels, know that it's going in the sequence RGB, RGB, HSO. And this is an HSO image of the Lagoon and Trifid Nebula. This is one of the images I'm genuinely happy with. The other one's absolute crap. Cool. But HSO is not the only thing. Hubble famously made the SHO palette. Do we all know what SHO means now? Sulfur in red, hydrogen is green. That's why so much green, oxygen in blue. A lot of Hubble pictures have that greenish blue purple look to them, not because real things are greenish blue purple. It's because they're doing the famous SHO palette. I can totally see. Both aesthetically, it looks cool. Scientifically, you can separate out the different elements very easily. So it has both aesthetic and scientific purpose. This is the classic HOO, hydrogen, oxygen, oxygen. This is much closer to what it would be to reality. You can get funky. You can get hydrogen, half sulfur, half oxygen, oxygen. HSOO. Now you're playing with what do you want out of the science? What do you want out of the art? Somebody in a forum from decades ago made something called a natural palette. Red is 75 sulfur, 25% hydrogen, then there's green oxygen, then there's blue is 10% hydrogen, then 90%. You can go crazy with it. I think this looks good. This is aesthetically pleasing and shows the different elements in different colors. So many different color palettes. These are not mine. This is somebody else's, but they made a little comparison on all of these. There are websites online where you can check all of these. So going back to what would you see with your naked eye? You know what? Let's talk about human perception for a second. In low light conditions, your cone cells don't work. You don't see color. When things are dim, you only see them in black and white. So are they truthfully black and white? I want us to disconnect from human perception being real. You can't feel force. You can't feel gravitational forces exerted by the earth. You feel the reaction forces from the ground. Your perception is flawed and limited, and your color vision doesn't work at night. So at night, through a telescope, if you brighten it up, this is what you would see. But that's not the truth. If you brighten it up and give it more color, that's what it would look like. Human body perception truth is not a thing, so we should not really concern with that too much. We haven't talked about the stars. I'll talk about the stars for a little bit. Stars are broadband targets. They're the closest thing we have to a black body radiation source. So they give out light in all different wavelengths. Narrowband, any kind of filter will cut out the colors of stars. So now if you really want to be good with astrophotography, you have to take a picture of the stars separately than your deep sky object. I have not done that yet. Is this painful? I am at this stage. Do I want to take this leap? The answer is always yes. It just happens a lot over summer break. This is how I feel sometimes with everything that I have to solve to get a good picture. Just showing this because you can see like red stars, blue stars, whitish stars. There are actually a huge spread of colors. So anyway, you take a picture of the deep sky object, use software to separate it out from the stars, work on that, take a separate picture of everything, cut out the stars, put it back in, make sure everything's lined up. This all takes a while. That's why I don't always do this. So going back to, can we take pictures like Hubble? We saw this Hubble picture. Here's my equivalent. Okay, now look. Any of you do art? Any of you do any creative endeavors? Can I see hands? What do you do? You paint. Do you like your old paintings? Do you have mixed feelings about them? What do you do?
Photography.
Photography.
No,
Do you like your photos from 15 years ago? 10 years ago?
Rarely.
Rarely. So
Sometimes.
you two might empathize with when I say,
Yes. Yeah.
I hate the photo I'm going to show you. You make your own judgment of it. I can't look at these, right? It's hard to look at your own stuff from here and like, what the hell was I doing? However, I still find this is crazy that I got ejecta from a black hole. What? From New Jersey with a DSLR camera. This is before I bought a cool camera. Here's M81, famous galaxy. Here's my one.
This is really cool.
The reds are hydrogen. Look at those red spots on Hubble. They set hydrogen to green. So I got the real color, they did the artificial color. But again, like I said, I don't want to get into the real artificial thing because it's a meaningless question to talk about. That one I think I'm semi-happy with. That's pretty cool. Here's the pillars of creation, very, very famous. Here's my one. I don't have the zoom power. Hubble used their tiny little sensor to get in. However, you can see the pillars of creation. Again, I grew up looking at this in a textbook. Let me zoom in. You can see the three fingers, right? Just right in the middle. That's the pillars of creation. My colors, I was still learning color processing at this time. Not
Where
that.
was that one taken?
This was 2021.
Where?
Oh, from Summit, New Jersey. Yeah. So from my backyard, not from a special place. This is what the like unstretched light frame looked like before I did color processing and stuff. I might go back and redo this. Insanely famous Hubble picture, the Orion Nebula. I got this one. Comparable. Highlights blown out. I did the thing. My photosite wells filled up. I lost all detail in the middle while there is shades of brightness here. So I needed to take a lower exposure to do this. You learn, you do, but it wastes multiple nights. Cool. So nothing ever truly compares to dark skies. This is taken last semester. I went to Death Valley. It's a Bortle 1, basically no light pollution. Took this image, you can see nebulae against the band of the Milky Way, processed this, and was very unhappy with this thing. I was like, oh, I guess somebody's headlamp or a car drove by and I got this giant light source. I was very sad because like it was insanely windy. We had one night to do this. I'm like, okay, what a wasted thing. Like, yeah, it's a cool photo, but there's a big bright light source. That is not a human-made light source. And you guys know this because I texted you all about this when I found out. So our solar system has all the planets going in a plane, like angular momentum, it's flattened down. There's dust in our solar system. Sunlight reflects off of that dust. If you're in a dark enough area, you can see the dust in the plane of our solar system. And that's what this is. I got an image from such a dark area that I thought what was light pollution was, yes, it was light pollution from the solar system itself. This was casting a shadow, which is freaky. Like sunlight reflected off of sparse dust spread across the whole solar system. Deep sky objects is what I do. This is a deep sky, standard deep sky object. Landscape astrophotography is something like this. Aurora from New Jersey, we're at a solar maximum. You can actually see aurora from New Jersey every now and then. I grew up wanting to storm chase. Now I've been aurora chasing for a few nights, right? Like I've invited you guys, can't time this out, but like it involves sitting in your car for 2 hours, getting frustrated, not seeing anything, and for 30 seconds something happens. And got to catch this from Clinton, New Jersey. There's solar lunar planetary. I don't do much of that, but when the solar eclipse happened, we actually went up to Vermont and took some. What are the prominences? See hydrogen mountains coming off of the sun. Transient objects like comets. We've seen comets together, John. This is a little video. Oh no, play video. There we go. This is a little time lapse of a comet from a couple of years ago, March 2020, deep pandemic times. However, you don't need all this equipment. This photo, taken with this phone, Samsung Galaxy, whatever, standard stuff. I set it, so again, I was in a dark site, right? This can't do filters, this can't do all that stochastic averaging out stuff. I was in a dark place. I set my camera to take a photo for 6 minutes, put it on a 10-second timer so I don't touch it. I just put it on the ground. This is why the framing is bad, because I couldn't see what I'm doing, but I just left it there, and this photo came out of my camera, if you consider that to be a little more truthful. Although no, these things are also secretly stacking. If you've ever done a hold your hand steady picture, it's actually taking 5 or 10 pictures and stacking them automatically. We're kind of in the feel free to ask questions. I have photos of how my setup has upgraded over the years. So that small camera with the small thing, everything gets bigger, need a bigger thing. How do you focus? Well, you need to buy a motor that you can control with the computer to focus so you don't touch it with your hand. Oh, hey, yeah, whoops, went back too far. This is us at the solar eclipse thing. This was a community astronomical event, which is a very different vibe to see people going around, kids getting excited, older people who've never done like getting excited with what's happening. So Diane was very gracious to invite us on her journey. This is our friend and colleague, Jesse Rivera, who's a professor at Swarthmore. I do a lot of my astrophotography with him. It's scary to be in the woods alone at night. I don't recommend it. We still hear weird. There was a deer that crept up to us like 5 feet while we were working with equipment and looked back. It was just like, what you guys up to? Terrifying. So our astrophotography journey went together. And yeah, this is a picture taken from Summit. This is one of my favorite images I have taken. This is there's a Wolf-Rayet star. It's this dying star that's shedding off its outer layer. So that's the star in the middle, and it's shedding off the outer layers. This is another star that died, and you're seeing the shock wave here. There's a lot of hydrogen. So this is HOO. You know what that means now, so you know what the colors mean and don't have to ask me if it's real or not. This is another very bright spot with a lot of oxygen, starlight reflected off of dust, a lot of hydrogen, a lot of heavier molecules that don't emit visible light. So those are the dark. So this is not the darkness of space. This is the darkness of smoke or dust that's blocking the light. That's it. Open for questions. I will leave it running on this.
Did you take this one in Summit also?
Yes. Summit, there was a outside place that I could place it, and it was within Wi-Fi range, so I could sit inside the office and control everything. I don't have that ability anymore since we moved to Westfield. Accessibility is a big deal, but yeah, how do you guys feel? Do you think you understand a bit more about what those pictures that you see up on walls or on things are, and at least the process of how to take them?
Yeah, for sure. Yeah, this was really cool. I didn't know that you could get these kinds of shots with your son. So.
Yeah, right? I didn't either. That's why.
I'm curious, with that rotating, like how it's rotating your camera, how fast is that rotating?
Okay, let's do this. How long does the Earth take to rotate once?
1 day.
That's 1 day, 24 hours. How many degrees is in one rotation?
360.
360. If you divide 360 by 24 hours, you get 15 degrees per hour. So 15 degrees is about that much. So that is how much it moves in 1 hour. Yeah. So pretty slow. Good.
I know it'd probably be hard, especially with all the equipment to get it there, but do you have any plans of going to like the Atacama Desert? Because I know that's like one of the best places for
Sure. Requires time away from school, requires money.
Well, I imagine it'd be very expensive.
Yeah, so like, you try to work it in. Like, me and my wife always wanted to go to Death Valley because we like those kinds of places. So I'm like, okay, that's a good astro spot also. Try to like wrap it up in stuff that you're already doing. So I have a like mini setup. My mini setup is just my camera, which is in my backpack right now with a lens and a mini tripod. The bigger motorized mounts, or the bigger your equipment, the more powerful your motor needs to be. So I have multiple motorized mounts for like a grab and go thing, or I'm doing a big thing. All these considerations. So yes, hopefully one day I get to go to these sites, but logistically it's difficult.
Speaking of like the picture you showed about that from that valley, do you have tips for like that kind of astrophotography? Because I tried that kind of astrophotography and failed miserably.
So I would say spending the $200 on a motorized mount is the single best investment you can do.
Okay.
A small one, get a little stand, like a little thing to hold your camera. Even your phone camera on a motorized mount will do a lot. So it's how much it's just get as many hours of exposure as you can. Okay. Because like once you get the data, I can go back to my old data from 2018 and reprocess it using the knowledge and the skills I have now and make better pictures. It's just that getting the best pictures when you are there. So we can talk detail. I'm happy to super talk details about all of this. I can point you out to. There are websites that do this better.
This is one thing that I want to ask because I think it's a funny question. It's very stupid, but I think
no such things.
When I tried, because actually I was trying to capture the aurora from Italy.
Uh-huh.
During probably
During the same
same
storms, it's the
the
same.
same solar storm
Oh.
that you captured in New
Yes.
Jersey, probably. And I had one problem. The aurora didn't show up in
Okay.
the night, so I wasn't
Sure.
lucky. But another problem that I had just at the sky, like shooting at the sky,
Mhm.
even with stocking,
Yeah.
was that my tripod was moving because it was very windy. How do you prepare for things like that?
So-
How do you keep it steady?
In the Utah picture, sorry, in the Death Valley picture, it was 50-mile-per-hour winds. There was a 1 hour break that I took that picture in. At the end of that picture, my tripod with my backpack hanging in a hook to weigh it down started tilting, and I was like, nope, this is few $1,000s of equipment. We're going. You can't fight wind. Do not try to fight nature. It will not work.
But you weighed it down with the
Yeah, but I got the gap in between the wind. As soon as the wind
Okay.
picked up, you can't fight it.
Okay.
And the bigger your thing gets, the more surface area the wind will get worse. There is no solution.
because
to
I
it.
bought a tripod specifically for that, and then I realized that I bought a lightweight tripod, but that meant
Even
that I
heavyweight,
have-
if there's genuine wind, you can't do like it
Okay.
doesn't matter if you have a lightweight or a heavyweight.
Okay.
You are not winning against wind.
Okay.
Yeah.
Thanks.
I'm curious about this portal ring. I guess it has.
Oh yeah, Bortle 1 through 7 is no light pollution to all the terrible light pollution.
So like to Newark, how does it compare?
Newark is like 8 or 9. Where I live, like about 30 minutes away in Summit or Westfield, wherever, was Portal 7. I drive an hour west in Clinton, New Jersey. There's Voorhees State Park, where New Jersey Astronomical Association is, so you can stay there at night and take pictures. No one will hassle you. That's technically listed as a Bortle 4, I think, because of city growth is now a Bortle 5. If you drive to Cherry Springs, which is about 6 hours away in Pennsylvania, you can get to technically what used to be a Bortle 1 or 2 and is now becoming 2 or 3. Also, don't get me started on Starlink satellites. They have ruined so many of my images. You'll get trains of 20 satellites just reflecting sunlight going. Humanity is at a terrible point where we are all thinking about individuals and not going back to headlights, going back to putting satellites up without consideration of how it affects the larger goals of humanity. I am in a not good state of mind because of all of this, and it all seeps into everything. Everyone is in a me, I have big lights so I can see better. I understand. You driving a bigger car also saves you while it kills the child in front of you. Please stop. Please fix your headlights. For the love of God. My whole talk was a secret headlight PSA.
That was where my question was going, like where's the best place in New Jersey to go? You said it very quickly, I think.
So
The state
New
park.
Jersey Astronomical Association in High Point, in Voorhees State Park in Clifton. That is a 40-minute to an hour drive from where we are right now. That's a decently good place. Also, the problem is most parks won't let you stay in after dark. This is an official site where they won't hassle you. Like, people go there, so you're not alone most of the time. Look up New Jersey Astronomical Association, go there.
But don't they generally want you to join if you're gonna, for a long time?
You can figure that out. Pay them the $40 a year that they need to keep running if you do use their facilities.
Plus bathrooms.
Plus bathrooms.
Yeah, wonderful talk, Sheehan. I agree, since as you point out, the colors are not directly what we might.
See, we can't see colors in the dark.
Yeah, so then what about UV? You make it, because a lot of the transitions are
Yeah, so I don't, commercially UV cameras
very expensive, are they, or?
probably available. I have not hit that level of astrophotography.
They
So
are
the-
a lot more expensive.
There you go.
They are
I am not
expensive,
low.
a
So-
lot more expensive. It's not,
So-
we're getting into a different
Yeah,
type of instrument.
Yes,
see, you know, because you do tiny photography.
And I don't have a UV camera.
yeah.
So it's
So-
like just to say it.
Yeah, so
Yeah.
but one thing, your cameras, like all our camera sensors, are sensitive to UV and infrared, and there's a filter on them to cut those out because we don't want that. Sometimes if you ever take a picture of a fireplace and you notice a purple glow around it, that's some of the infrared leaking through. So these Astro cameras don't have that filter on them. So I am getting a little bit of UV on the edges and a little bit of infrared on the edges, but as you said, that is a completely different thing.
You can get X-ray cameras, but
Sure, yes. How do you focus X-ray light?
People figure it out.
I know they use mirrors to skim it off, but then yes, Chandra X-ray telescope exists, but no.
And are there also like films that down convert, like, that you put in the high? I mean, like there's materials that do, half harmonic generation kind of thing, like if
Sure.
you put in a high frequency and you get half the frequency out.
Oh, okay, sure.
People use those?
I don't know. This is still the enthusiast astro community that I'm part of, so
So if I can comment, you need the high intensities for second harmonic generation.
Yeah.
And
okay.
here, this is an application where you have very little
That's
light. Right?
this
What
is
you
all
can
very
think
little
of
light.
is, try to think of something like fluorescence screen. But then the problem with fluorescence screens is that you get straight light in and you get diffuse light out.
Mm.
So sort of
It's all fuzzy
you basically lose
detail.
yeah, you basically lose the resolution. You sort of throw away some of the light because the light will actually go in 4 pi.
I see.
Even with high NA, you will actually lose at least half of the light, if not, sort of 9% of the light.
Mm.
So it's
Yeah, no. it doesn't-
imaging outside the visible
Yes.
is
this-
sort of I think takes everything up in cost therefore by 120. So
All right.
Can I ask a quick question?
Yes, go ahead, Michele.
So great talk. And so the way I'm thinking about this stacking is that really all you're doing is to averaging or adding images still in
Yes.
one after the other. So one thing so this made me think about in high performance computing, something that happened maybe a decade ago or so is that people started making available their own like regular home computers or their office computers
Mhm.
for like helping others carry out computing when protein folding was still an issue.
Right. So stacking is not at that level. Like we don't need that level of computing.
But no, what I'm thinking is, could you use that same idea and like take all the pictures that have ever been taken of the sky?
Yes, there are projects like this.
Okay.
I guess the question is that your artwork now?
Oh, no, I'm just
Yeah.
after like the perfect picture, right? No, it's not
Yes.
about like, yeah.
So yes, the perfect picture. So there are astrophotographers who are like collaborating together. Everyone is taking the same like degrees in the sky, same field of view, and then stacking all of their pictures together. So there are collaborative efforts like this. However, then the problem is like, well, Hubble can just do that in one go and do something better than you.
Yeah,
I get
maybe.
this.
Hubble is
Yeah,
also
but
very
people do
expensive.
it. People absolutely do it.
Hubble is super expensive, but like there are 7 billion people with a cell phone on this planet. So I'm wondering, like, yeah, would that work? Like, can
Like
we
I said, people have been doing that, and I know it does work. It comes with its own challenges of getting a lot of people to do the same very technical thing that you want them to do. But there are definitely collaborations. There are even science collaborations where they have clusters of telescopes that are effectively just off-the-shelf DSLR cameras and lenses that you can buy that they have running in Australia and Europe and blah, blah, blah. And they're combining all their data and pretending like it's a much larger telescope, the same way like radio telescopes do it, right? You can do a little bit of interferometry to figure weird stuff out and make it behave better than it should.
Thank you.
Sorry, Sheehan. So I'm going to be a bit annoying. I'm
Yeah,
going
go
to
ahead.
ask you a question about image processing.
Yes.
So, how much do you think it's possible to take the images from your presentation
Uh-huh.
and adjust them such that they look good even with the room lights on? So,
I understand.
so basically sort of, here you use the trick of turning the lights off so that you get more
I
light.
already
in the
did that.
So this is already maxed out.
This is already worse than they actually are because projectors don't have a high dynamic range. What our human eyes possess that no camera does is a gigantic way of seeing both super dark things and super bright things at the same time. Projectors are worse than screens. So I had to basically destroy all the images as I put them over here and made them worse so you all could actually see the details in them. They look terrible. So yes,
So just that everybody knows these are terrible images.
that's how I feel about them most of the time. But like I said, anyone who's making art might feel the same way. It always, some of them are. I'm really happy with this. I'm really happy with those last two pictures. Those are some of the. Solar has some issues in it, but I'm learning. Yeah, but come on. Oh God, it's struggling to get through. Yeah, these two I'm genuinely incredibly happy with. There's a big problem with this image, but I'm not going to tell you all. You won't find it. Jesse knows. He's my astrophotographer friend. He can see and pick it up, but I'm not telling any of you. I do have to teach in 15 minutes. So, but like, yeah, one question, but then I can't stay for food after this.
How much of an issue is like moisture in the air or like this level of
Yep. So you get dew forming on all your equipment and your sensors and stuff. So there's heaters. So now you need extra power to run those heaters. Dew heating is a whole thing. So I have like heaters wrapped around all my telescope setups. The cameras themselves. The cameras have a cooling unit to cool the chip while there's a heating unit in front of the chip. It's preventing water from condensing. And those things leak oil, and then you have to clean them, and it never ends. It's a frustrating and painful and very fun hobby that mixes science and art and many other things together, which I like, which I enjoy.
How about further about cooling and also warming the camera, make or form crystals in this interview?
Yes, you're getting into the weeds. There are forums and forums of people talking about like, oh no, I froze some water on my sensor. What do I do? All these things happen everywhere all the time.
This is a quick question. Okay, this is an 8.7-hour exposure. How much time did you spend after doing this to make this image?
Another 4 to 8 hours. Because like you make an image and you start getting, if any of you again worked on an art project or anything, you work on it for 4 hours and then your eyes are glazed and you're like, I have no objective sense of what looks good or not. So you have to walk away from it and come back the next day and you're like, what was I thinking? Let me start over from the beginning. And you're controlling all these values. And at a certain point, you're like, I give up. Nobody else understands what I'm talking about. If I'll show my wife and she'll be like, this looks great. I'm like, it doesn't. The panels didn't line up right, and there's an error line going through it that they're not picking up what I'm seeing. And anyway, so it's the goal. It's 50% outside, 50% inside is how it usually works out.
What is the program that you use to reduce the images?
There are many. You can Google these, but like a lot of them are free. Deep Sky Stacker to stack the images, Photoshop to stretch and put all the things together. But PixInsight costs a lot of money, $250, which is the much more scientific way, but you need a lot of training, like a lot of tutorials to use that. Affinity Photo is free and replaces Photoshop, which might be a good thing. Serial is the new one that you've started playing with. Serial is nice. I haven't had the time to play around with Serial yet, but I will. There's a lot of choices of a lot of free software out that can do all of these. At least give you the process for doing it, and then you have to do it for yourself. Cool.
Let's thank Sheehan.